this is question 7 from the 2019 Leaving Cert paper, based on acids and bases in pH. Okay, so we'll have a quick run through it, and we'll start with part A. Alright, use equations to show that when dissolved in water, HCl acts as a Bronsted-Lowry acid and NH3 acts as a Bronsted-Lowry base. Okay, so according to Bronsted-Lowry theory, an acid is a proton donor. Okay, so if we have HCl dissolved in water, so water is going to be H2O plus HCl. Okay, and we're going to have H3 plus Cl minus. Okay, so hydrogen donates a proton, donates a H plus to the H2O. Okay, and you have H3O plus. Okay, so HCl there is acting as an acid as it is donating a proton. And then if we look at the second part, so H2O plus NH3, base is a proton acceptor. So here we're going to have NH4 plus plus OH minus. So there are two equations we need for part 1 and part 2. Part 3 then is explaining why HCl has a weak conjugate base. So HCl is a strong acid. It easily donates a proton. It is a good proton donor. So that would be the main one that we'd look at, really. I suppose that would be the first one. We'll go through the various other reasons, such as the forward reaction here being favoured rather than the reverse reaction, and we can go into equilibrium. But if we know that if something is a strong acid, it easily donates a proton, its conjugate base is going to be a weak base. Okay, and then we have NH3 has a strong conjugate acid. We know that NH3 is a weak base. Okay, and its conjugate acid we see from the equation is NH4 plus, and that will easily donate a proton, so it is a strong acid. Okay, so NH3 is a weak base. It's a poor proton acceptor. Okay, if you want to go into equilibrium, but you can avoid it. The reverse reaction is favoured because equilibrium lies on the left. Okay, and that would be question A. Now, if we go on then to part B, it says pure water self-ionizes as follows: 2H2O, and then you have H3, H3O plus and OH minus. The ionic product of water, Kw, measures the extent of this self-ionization, and a table of the Kw values is given there to the right. So it says write the self-ionization constant Kw expression for water. Okay, so there we can have Kw is equal to concentration of H2O plus. Okay, it's important that in brackets R squared. If it's not square, you lose 3 marks. And OH minus. Okay, that would be according to the equation they give there in the question. I'd say just to go with that. But another acceptable equation is H plus and OH minus. Okay, that's also acceptable. Okay, the next part of the question then, are the data in the table consistent with self-ionization of water being an exothermic or an endothermic process, and justify your answer. Okay, so I'm just going to answer this orally. Okay, so it's an endothermic process. As the temperature increases, there are more and more ions. So you see here as you work your way down your table, as the temperature increases, so too does the ionic, the ionic product of water, meaning there are more ions present. Okay, so the forward reaction is favoured by the increase in temperature, so the equilibrium shifts right. Okay, we should know that in the ionization of water, equilibrium usually sits on the left, as there's a low concentration of H plus and OH minus in water. Okay, as temperature increases, that concentration of H plus and OH minus increases, so equilibrium shifts right. Okay, so this is an endothermic process. Now the next part is part 3, so plot a graph of Kw versus temperature. And it's interesting the way that question is phrased, because usually when we'd be drawing a graph, we would go and we'd have our independent variable on the x-axis. So you would expect that you'd have temperature along the x-axis, and you'd have what changes, which is the ionic product of water. It's what you're measuring. Usually that would be on the y-axis, but in this question it says plot a graph of Kw versus temperature, so x versus y. So in this particular use, they were actually looking for Kw along the x-axis and temperature along the y-axis. On the market scheme, they did actually accept both. They were both acceptable answers, and I have both of them done over here. So this would be what you would normally expect, the version on top there, but the one on the bottom is actually the one that they were looking for. Okay, so I'm just going to move this over so we can work with it. Okay, so that's plotting the graph. Okay, use your graph to predict the value of Kw at body temperature 37 degrees Celsius. So all you have to do there is get a ruler, go to about 37 degrees Celsius, which would be in and around there. Okay, so from 37 degrees, move in. Just trying to get this straight. Now, okay, and where that meets your graph, we're just going to draw a straight line down. As close as I can. Okay, and that comes out to be about 2.3. Okay, so that's about 2.3 by 10 to the minus 14. So that's our answer for part 4. The range of answers given was between 2.1 and 2.5 by 10 to the minus 14. Okay, so anywhere inside that range would have got you your answer, or your marks. Next then we have part 5. Use this value to calculate the H3 plus H3O plus ion concentration of pure water at 37 degrees Celsius. Now, a little bit of work I suppose you need to do in order to be able to calculate that. We know that Kw is equal to H plus by the concentration of OH minus. Now, in water, the concentration of H plus and of OH minus is basically the same. Okay, it is the same. Okay, there's a very, very little difference in the two. So what you can actually say for this part of the question is that kW is, it could also, if they're both the same, well then you could represent it as h plus squared. If you're looking for your concentration of H plus by itself, then the answer you're looking for is going to be the square root of kW. I hope that makes sense. Okay, the kW figure we got in the last part of the question was 2.3 by 10 to the minus 14. Okay, and that gives you an answer of 1.51 by 10 to the minus 7. Okay, that's your answer for part 5. And for part 6 then as well. Oops. Okay, the pH of pure water is close to 6.77 at one of the temperatures in the table. Find by calculation this temperature. Now, okay, so here's where our pH is coming in. So to find pH, minus log to the base 10 of H plus. Okay, that's what we want. In the question, however, we're given the pH. We know the pH is 6.77. So that's equal to minus log to the base 10 of H plus. Now, if we have pH, alright, we treat this as like we would any other, I suppose, mathematical term. Alright, we need to find H plus. Okay, so we need to, what we do is we actually find the antilog. Okay, so all you have to do to find the antilog on your calculator is press shift and then press log. What will come up it will look like basically 10. Okay, it will come up on your calculator. You type in, because it's minus log to the base 10, it's going to be minus 6.77. Okay, so that is your antilog, it's called. Okay, so that is okay, so this is how it will come up in your calculator. Okay, but make sure it's shift log, that you don't just put 10 to the power of minus 6.77. Okay, and that then in your calculator comes out to be 1.69 by 10 to the minus 7. Okay, they accepted 1.7 as well, the rounded figure. Alright, kW then is what we're asked. Well, we're asked to find the temperature, but on our graph we have kW and temperature. So here we're able to find kW and then we'll be able to find our temperature. kW, again, H plus. Okay, these are the same, so both the concentrations both are the same. So it's going to be basically 1.69 by 10 to the minus 7 squared, or 1.7. And that gives you an answer of 2.9 by 10 to the minus 14. That's our kW figure. And we have kW, so now off our graph we can find our temperature. So we have to go to 2.9 by 10 to the minus 14. So if we go to 2.9, okay, so if we go to 2.9, it's going to be about there. Draw a line straight up. Okay, and our answer is going to be 40 degrees Celsius. Okay, yeah, and also that answer 2.9 by 10 to the minus 14 is in our table, so we know it's definitely 40 degrees. Okay, and that's the answer to the final part of the question.